Okay, here are the notes for section 6.1, which deals with vectors in the plane. So first we talk about two-dimensional vectors. So it's the ordered pair of real numbers a comma b, not only in terms of point in the plane, it's also in terms of directed line segment, an arrow, with its tail at the origin, the head at the point a comma b. So a is any x value, b is any y value. How long that arrow is referred to as magnitude. The direction in which it points is the direction. Because in this context, the ordered pair AB represents a mathematical object with both magnitude and direction. We call it the position vector of AB, denoted as a comma b within angled braces, to distinguish it from the point a comma b. So parentheses represent a point, angled parentheses represent a vector. Down here, you got the fancy math definition of a two-dimensional vector. Two-dimensional vector v is an ordered pair of real numbers denoted in component form as a comma b. The numbers a and b are the components of the vector v. The standard representation of the vector is the arrow from the origin to the point a comma b. The magnitude of v is the length, and the direction is the direction in which the arrow is pointing. The vector 0, 0, 0 is called the zero vector, has zero length and no direction. One thing to be careful of is that two arrows with the same length and pointing in the same direction are the same vector. You can move the vectors around the coordinate plane all you want, and they're still the same vector. A vector is a set of directions. Okay, so the figure below shows the vector 3, 4, represented by RS, an arrow with initial point R and terminal point S, as well by a standard representation OP. So they are the same vector. So 3, 4 essentially gives you the directions. It's 3 spaces left, 4 spaces up. But where you start and where you end doesn't actually matter, as long as there are 3 spaces left, 4 spaces up. So this rule is used to find the component form of a vector if you know its initial and terminal points. So if a vector has initial point x1, y1, terminal point x2, y2, given by this vector, difference in the x's, comma, difference in the y's. So prove the arrow from R to S is equivalent to the arrow from P to Q. So for vector RS, we would have x2 minus x1, oops, should be an angly bracket, comma, y2 minus y1. So this is going to be -1 plus 4. So that's 3, and that's going to be 4. So there's RS. And for PQ, similar thing, x2 minus x1, comma, y2 minus y1. So that's 3, comma, 4. So same vector. To go from this point to this point, you go left 3, up 4. To go from P to Q, you go left 3, up 4. Okay, so the magnitude of vector, or the size, is represented by this formula. This may be familiar. This is the distance formula, because essentially you're measuring how long the vector is. It's represented by absolute value bars around your vector name. If you already are in component form, it's just a squared plus b squared, because a is already x2 minus x1, and b is already y2 minus y1. So for 2 here, find the magnitude of the vector PQ, where P is this and Q is this. So the first thing we need to do is figure out the vector PQ. So vector PQ is x2, -5, minus x1, -3, comma, y2, minus y1. So this vector is -2, comma, -2. So 2 spaces left. Now you can think about this. To go from -3 to -5, I need to go left 2. To go from 4 to 2, I need to go down 2. So since I'm in component form, the magnitude of PQ is the square root of a squared plus b squared. So that's the square root of 4 plus 4, which is the square root of 8, which is 2 square root 2. All right, so vector operations is how we combine vectors. So the algebra of vectors sometimes involves working with vectors and numbers at the same time. In this context, we refer to those numbers as scalars. So a scalar is a number that does not have direction and magnitude. So it's 2 is a scalar, 7 is a scalar. So let u be some vector u1, u2, v is some vector v1, v2, and k be some real number or a scalar. The sum of the vectors u plus v, you just add up the corresponding components. If you have a product, the scalar just distributes inside. All right, so the sum of u and v kept represented geometrically by arrows in 2 ways. The tail to head representation The standard representation of u points from the origin to u1, u2. The arrow from u1, u2 to, then you do the combination, represents v. The arrow from the origin represents uv. So that's this method. So u starts at the origin, goes to some point. V begins at that point, goes here. So the resultant is the one that goes from the origin to the end of v. The parallelogram representation, both of them are in standard position. So both of them have their initial point at the origin, and you're drawing the diagonal, essentially, of a parallelogram. So diagonal, which represents uv. Now, oops, lost that. It should be a little angly there. So u plus v. So if we're adding angles, we can just add matching components. So u plus v is given by -1 plus 4. Add the x components. 3 plus 7, add the y components. So this is vector 3, comma 10. So if I follow vector v, then follow vector u, then v, I'll end up at the coordinates 3, 10 if I start at the origin. 3u is 3 times -1, comma 3, which is -3, comma 9. The 3 just distributes. So 2u plus -1v, well, that's 2 times u plus -1 times v. So distribute -2, comma 6 plus -4, comma -7. So, and then you would add matching components, -2 plus -4, comma 6 plus -7. So that's going to be -6, comma -1. We've now resultant. All right, so we got unit vectors. A vector u with length 1 is referred to as a unit vector because it's 1 unit long. If v is not the zero vector, 0, 0, then the vector u is given by a vector divided by its own magnitude, or the vector v times the reciprocal of its magnitude. Either way works, just depends on how you prefer to think about it. So as a unit vector in the direction v, often called a direction vector, because it has length 1 but still points in the same direction that v did. Any vector in the direction v or in the opposite direction is a scalar multiple of this unit vector. So find a unit vector in the direction of v and verify that it has length 1. So the first thing we need to do is figure out the magnitude of v. So the magnitude of v is given by the square root of a squared plus b squared. So that's the square. 9 plus 4, so that's root 13. So the unit vector is going to be your original vector divided by root 13. So it's going to be -3 over root 13, comma 2 over root 13. But we do not leave roots on the bottom, so this is -3 root 13 over 13, comma 2 root 13 over 13. So that's my unit vector. Verify as length 1, so I need to find the magnitude of this vector. So the magnitude of u is given by the square root of -3 root 13 over 13 squared plus 2 root 13 over 13 squared. So this, let's see here. If I square that fraction, that's 9 times 13 on top, because the root goes to the 3, gives me 9, root goes to the root, which cancels it out. So 9 times 13. So this is 117 over 169, plus, that's going to be 4 times 13, which is 52 over 169. So if I add those up, 117 plus 52 is 169 over 169, which is root 1, which is just 1. So the unit vector has length 1. So there are some special unit vectors. The unit vector I, which is 1, 0, and j, 0, 1 are the standard unit vectors. Any vector v can be written as an expression of the standard unit vectors. So a, b becomes split into a, 0, and 0, b. So you separate the x and y components. Then you factor the a out of the first and the b out of the second. 0 divided by b is still 0. And then this is a unit vector I. This is unit vector j. So just sometimes instead of seeing your vectors written as a, b, you'll see ai plus bj, which gets to be a little more helpful when you do some more advanced vector arithmetic. So They are the horizontal and vertical components. Okay, direction angles. A simple but precise way to specify the direction of vector v is to state its direction angle theta that v makes with the positive x-axis. Using trig, we can see the horizontal component of vector v is v cos theta, and the vertical component is v sine theta. Solving for these components is called resolving the vector. So resolving is undoing a resultant, essentially. So if v has direction angle theta, the components of v can be computed using the formula. So here's your horizontal component at magnitude times the cos theta, magnitude times the sine theta. So find the components of the vector v with direction angle 115 and magnitude 6. So the horizontal component is given by the magnitude times the cosine of the angle, which would become 6 cosine 115. Make sure my calculator's in degrees. So this would be negative 2 point, we'll call it 54. The vertical component is v sine theta. So 6 sine 115. So that is positive 5.44. So those are my two components. All right, so here, find the magnitude and direction angle of each vector. So the magnitude is not too terribly tricky. It's going to be, so the magnitude of u is given by the square root of a squared plus b squared. So that's root 9 plus 4. So the magnitude is root 13. Now, to find the angle, this is the magnitude. So the horizontal component, 3, is equal to the magnitude times the cosine of the angle. So if I divide that across, I get 3 over root 13 equals cos theta. And then do the inverse cosine to get theta by itself. So let's see here. So 3 divided, well, inverse cosine of 3 divided by the square root of 13 gives me a theta value of 33.69 degrees. So the other way to think about it, if you think about what the vector does, this is, this is A, this is B, there's my angle. Theta is equal to the inverse tangent of B over A. Because if we set this up, tangent theta is B over A, so it's solved. Now, there are some cases in which you need to do some trick to it, which is probably going to show up down here. All right, so the magnitude of V is equal to the square root of negative 2 squared plus negative 5 squared. So that's root 4 plus 25, which is root 29. So theta is the inverse tangent of B over A. So the inverse tangent of negative 5 divided by negative 2 gives me, if I work this out, I get 68.1, we'll call it 2 degrees. But that can't be the angle. This angle is in quadrant 1. This guy lies in quadrant 3. So I need to actually add 180 degrees to flip it around, get it to pointing the right way. So the direction angle for this is actually 248. Because these are both negative, when I do the tangent, it thinks the coordinate is up here because the two negatives cancel out, vertically 5 over 2. But the point is actually down here. So that's 180 degrees around the circle. So you have to pay attention to where your angle actually is. Typically, if this value on the bottom is negative, you will need to add 180 to your answer to flip it to the right quadrant. But you should always just check the math to make sure. Actually, will that always happen? No. We'll see. You should look at the graph just to be sure. Okay, application to vectors. The velocity of a moving object is a vector because velocity has both magnitude and direction. The magnitude of velocity is the speed. So example 7, a DC-10 jet aircraft flying on bearing 65 degrees at 500 miles per hour. Find the component form of the velocity of the airplane. Recall that the bearing of the angle of the line travels due north. Measure it clockwise. So this angle is 65 degrees, but normally when we do calculations, we measure this angle, which in this case would be 25 degrees. So actually, it's flying more like this angle. If that's north, and this is due east. So this, I actually already know the magnitude. That's how fast the thing's going. So find the component form. So the component form, so the horizontal component is the magnitude, 500, times the cosine of my angle with the horizontal. The vertical is the magnitude times the sine of my angle with the horizontal. So 500 cos 25, 453.2, 500 sine 45, or not 45, 25, 211.3. So the component form is 453 point, oops, try that again. 453.2, comma, 211.3. So there's your component form, horizontal, comma, vertical. Okay, so example 8. Pilot Aisha Saunders' flight path as they're leaving San Francisco International, flying in Boeing 727 due east. There's a 65-mile-per-hour wind with bearing 60 degrees. So that's from the vertical, so 30 degrees from the horizontal. Find the compass heading Saunders should follow and determine what the airplane's ground speed will be, assuming that a speed with no wind is 450 miles per hour. So we're going to have to be a little bit clever here with how this works. So let's see here. What do we know for sure? So, let me think here. So, they want to end up going due east. The wind is blowing this way, which means the plane needs to be aiming down that way a little bit. So, let's see here. So we need to find essentially the angle from north. We need to find the angle that this vector makes. So assuming the speed with no wind is 450. So I know the magnitude of this vector is 450. I know that the wind speed has a magnitude of 65. So let's see here. So we'll call this wind, we'll call this plane. So this angle here is 30 degrees because it's 60 degrees from north. So I know that the wind plus the plane, so the wind's vector is 65 cosine 30, comma 65 sine 30, plus the plane, 450 cos I don't know, comma 450 sine I don't know. And this will give me my resultant vector. Now, since I'm flying due east, this total of the y's has to be 0 because due east does not have this. So I know that 65 sine 30 plus 450 sine theta has to be 0 because otherwise it doesn't work out. So let's see here. So this is 450 sine theta equals 65 sine 30. So sine theta is 65, whoops, this should be 30. Sine 30 over 450, and then do the inverse sine, so we'll actually come this way. So theta equals the inverse sine of 65 sine 30 over 450. So calculator time, 65 sine 30 divided by 450, inverse sine of that. So this angle, the plane is on a bearing of, so that angle is 4.1 degrees, but it's 4.1 degrees down, so the bearing is 90 plus that. So 94.1 degrees would be the bearing. and I lost a sign somewhere, that should be negative, which means that's negative, which means that's negative, which means this is actually negative, so that's why it's a down rotation. Okay, let's see here. Determine the airplane's ground speed will be. Okay, so the ground speed is the magnitude of the resultant vector. So this stuff is all 0, so it's just this part here. But I know what theta is. So theta is negative 4.1. So let's see here. So the speed equals the magnitude of 65 cos 30 plus 450 cos negative 4.1 all squared plus 0 squared, because I know these two add up to 0, the whole point of that. So let's see what we got. So essentially that goes away, that cancels that, so I'm left with just the 65 cos 30 plus 450 cos negative 4.1. So 65 cos 30 plus 450 cos negative 4.1. And the speed comes out to be a whopping 505 miles, 0.1. So there's my bearing, there's my speed. Okay, and example 9 here, let's see here. So a force of 30 pounds just keeps the box in the figure from sliding down the ramp inclined at 20 degrees to find the weight of the box. So we know that this force here, AD, has to be 30, because the box is trying to slide down, so we have to push up with 30. Find the weight of the box. So let's see here. So AB is the weight. Okay. So if you notice we've got a rectangle here, if that's 30, that's 30. There's my weight already labeled. So if I look at this triangle, the sine of 20 degrees is equal to 30 divided by the weight. So the weight is equal to 30 divided by the sine of 20. So let's see here. 30 divided by the sine of 20. So the weight of this box is 87.7 pounds. And that brings us to the end of the section.